Alright, so now we've finished this unit, so I have a few problems to practice through, work through, and see just how well you understand integrals. So, first I have an opener for you. Evaluate this integral, which looks really complicated, but I think it's really worthwhile if you hit pause, spend a few minutes trying to work it out, and then hopefully come up with something, and whether you do or not, then go ahead and play and I'll work you through this. Okay, so here we go. We're trying to do this integral and it looks way too complicated. We could distribute the numerator and then separate it into different fractions, but that seems a little too complicated as well. So let's zoom out a little bit and look at this. And when you look at this, does it remind you maybe of the quotient rule, which is u prime v minus uv prime over v squared? Well, maybe it would help if I rewrote this integral. And I wrote it as e to the x minus 1, minus e to the x times 1. And then the denominator, we could factor that, and that actually factors to x minus 1 times x minus 1, which I could write as x minus 1 squared. And now, it really looks like it fits that pattern. So, what is the v? I think that would be the easiest to identify. So the v is going to be x minus 1. And then what is the u? Well, look in the numerator. The u is right here and the derivative of u is right here. Well, e to the x is its own derivative, so u is e to the x. So I think we've got it now. So the antiderivative of that is going to be the quotient e to the x over x minus 1, plus any constant. Go ahead and differentiate that and make sure you see that that's what you would get when you found the derivative of this, that you would come up with that. Alright, but that wasn't the real opener. Here's the real opener. I'd like you to use 4 upper and 4 lower rectangles to find rational numbers a and b such that the integral from 0 to 2 of 4 minus x squared dx is between a and b. So in other words, we want to approximate this integral. One of them is going to give me a lower value than the actual answer, and one of them is going to give me a greater answer than the actual answer. So we haven't done these in quite a while. At first, before we knew what and how to actually do integrals, we approximated them using rectangular approximations. And then we learned that the more rectangles we had, the better the approximation. And eventually we thought of, if we look at the limit as the number of rectangles goes to infinity, if that exists, that would give us the exact answer, and that led us to proving the fundamental theorem of calculus. Alright, so let's go back to the beginning. What does this function look like? 4 minus x squared. Well, that looks like a parabola. And let's put our x-intercepts on there. And so another way of thinking of that, if I rearrange it, it's negative x squared plus 4. So that's a parabola that opens downward, and it's been shifted up 4 units. Close enough. Alright. So the integral from 0 to 2 is trying to approximate that area. So let's use some rectangles, and it asks to use 4. And so first of all, we have to figure out what's the width of our interval. Well, that's 2 units long. So if I'm going to split it up into 4, that means that the width of each rectangle is going to be 1/2 or 0.5 units. Now, if I want rectangles that underestimate this, then for my first rectangle, which goes from 0 to 0.5, I'm going to want to choose the right endpoint to evaluate the function, and that's going to give me a rectangle that'll underestimate. So I want to use the right-hand endpoint of each subinterval. So let's write this as L4 for 4 lower rectangular approximation. And the width of each rectangle is going to be 0.5. And the height, I'm going to multiply that by the height of each rectangle. So for the first rectangle, I want to evaluate my function at 0.5. And then, maybe I won't factor it out yet, so that'll make it easier for you to follow. So 0.5 for the width times the height. And then the second rectangle also has a width of 0.5, and I'm going to multiply that by the height of the function. Now I'm looking at the interval from 0.5 to 1. If I evaluate it at 1, that'll be the lowest value of my function on that interval. Okay? And then the third rectangle will also have a width of 0.5, and then I'm going to multiply that by the function value at 1.5. And finally, the last rectangle is going to be 0.5 times the function evaluated at the right end point, which is 2. So you notice I could factor out the 0.5, and then I need to evaluate f of 0.5, and then f of 1, and f of 1.5, and f of 2. Now we could use a calculator, but oh, that's just a waste of time. We can do this in our heads, right? 0.5, wait, what was my function? Y equals 4 minus x squared. Or negative x squared plus 4, either way. Okay, so 0.5, that's going to be 0.25. 4 minus that gives me 3.75. Okay, f of 1, that's easy, that's 3. F of 1.5, 15 squared, is 225, so 2.25. 4 minus 2.25 is 1.75. And then f of 2 is going to give me 0. So for my lower approximation, I'm going to do 0.5 times the sum of all these, which is 6.75, 7.5, 8.5. And so half of 8.5 is 4.25. So that's my lower approximation. Now let's do the upper 4. So for this, I'm still using 4 rectangles, so the width of all the rectangles is still 0.5. I'll factor that out of all the heights. So for the first subinterval, I'm going from 0 to 0.5, and well, maybe I'll just draw it again here for you so it's easier to see. 1, 2, and then this is 4, and my function is coming down through here. And so I'm splitting this up into 4 subintervals. So my first rectangle goes from 0 to 0.5. I'm going to want to choose 0 to evaluate the height of my rectangle. And that'll over-approximate. And then when I go 1, this is 0.5, this is 1.5. And then when I look at the interval from 0.5 to 1, I'm going to want to choose f of 0.5 to approximate the height of my next rectangle. And then the interval from 1 to 1.5, I'm going to use 1 to approximate, f of 1 to approximate the height. And then from 1.5 to 2, I want to evaluate it at 1.5. So all those rectangles are going to over-approximate. So I'm going to do the first subinterval, I'm going to evaluate at 0. The second one from 0.5 to 1, I want to evaluate at 0.5. And then the next subinterval from 1 to 1.5, I'm going to evaluate it at 1. And the last subinterval, I want to evaluate at 1.5. Alright, well, I already calculated most of these numbers. I didn't do f of 0. So f of 0 plugged into this function gives me 4. F of 0.5 was 3.75. F of 1 was equal to 3. And f of 1.5 was 1.75. So we have for our upper limit 0.5 times, they'll just be adding 4 to that, so 12.5. And half of 12.5 is 6.25. So I know using 4 rectangles, my over approximation would be 6.25, and my under approximation would be 4.25. So going back here, That means that, let's use a different color blue, for A, 4.25, and for B, 6.25. And there you go. Alright. Well, since we've done so many openers, it would only make sense to finish with a closer. So let's look at this one. And once again, I would hit pause, think about it, try it on your own for a few minutes, and then come back and hit play. Okay, so this is telling us a value for a function g at 2 and at 3, and it wants us to calculate the integral from 2 to 3 of g prime of x minus 1. So we haven't seen a problem like this, but yet you should understand enough about integrals to be able to do this. And so that's the biggest thing that you have to understand going forward in mathematics. If you understand conceptually, when you see a problem that you don't recognize, that you haven't done before, you have to trust that you know enough to figure it out, instead of being in that mode of, I don't recognize it, I can't do it. So we can do this. So let's focus here. It's a definite integral. We've done a lot of definite integrals. So what do? We have to take the antiderivative and evaluate it at the limits of integration. All right, so what's the antiderivative of g prime of x minus 1? Well, g prime of x is the derivative of a function, so the antiderivative, wouldn't that just be g of x? And then the antiderivative of 1 is just x. So we're going to evaluate that from 2 to 3. So I'll plug in 3 first, and I get g of 3 minus 3. And then subtract from that, plug in 2, g of 2 minus 2. Oh, and all of a sudden it seems very simple. We know g of 2 and g of 3, they gave it to us in the problem. G of 2 is 4 and g of 3 is 5. So we have 5 minus 3 minus 4 minus 2, which is 2 minus 2, which is 0. All right. So for review problems in 18A, remember you're supposed to do that without a calculator. In 18B, some of those require a calculator. And then I also picked out 2 problems from section Review C.